So I'm Lena Voita. I'm a research scientist at Yandex and a PhD student only at two universities. It's Amsterdam and Edinburgh. It's Zurich, it's from RICOS affiliation. Today we will try to understand how representations of individual tokens in the transformer evolve between layers and the different training objectives. So this talk is based on our AMLD paper, which was joint work with my research parents, Ivan Titov and Jika Sendrich. But before we start, I want to give you some context for our work. As you probably know, one of the most noticeable and influential events in NLP in the last couple of years was transition from pre-trained word embeddings, such as GLAV, Word2Vec, FastText, to pre-trained contextualized word representations. Initially, it was proposed in the Edinburgh paper. So the idea was really simple. If we can make use of pre-trained word embeddings, why don't we make use of pre-trained model, which can give not only embeddings for words, but embeddings for words in context of sentences they appear in. So sounds reasonable, and therefore took bidirectional LSTM and trained it as a language model. After that, for different tasks, such as reference resolution and question answering, they took a task-specific architecture, which was state-of-the-art at the moment, and injected these contextualized representations from language model. And immediately they got very noticeable improvement for all tasks. A bit later appeared BERT. It used different architecture, transformer instead of LSTMs, and a new training objective, mask language modeling, which I'll explain you in detail a bit later. But the most interesting was how they used a model. So the model was used instead of all task-specific architectures. Well, Elmo representations were injected in different models for each task. BERT eliminated the need for task-specific architectures whatsoever. And it was the beginning of a very long story. Of course, there was a race for better scorers, trying to come up with better training objectives, better training strategy, better fine-tuning strategy, and a lot of works tried to understand what these models learn. The most popular approach for analyzing representations is to use problem classifiers. These classifiers are trained to predict some linguistic property from frozen representations. For example, part of speech text is shown on the picture. Alternatively, we can look at the mechanisms a model uses to encode information. For example, if we're dealing with transformers, we might be interested in attention mechanism, in importance and roles of different attention heads in the model. And this is illustration from our ACL paper, where we showed that the most important heads in transformer often play linguistically interpretable roles. Another approach to understand what a model knows is ask it to fill the blanks. In this way, we can, for example, understand which facts a model learned. Here, for example, is a sentence, direct X is developed by, and then a model is asked to predict the token. These were results for specific models, and unfortunately, there is still no general understanding of the processes which shape representations. What I want to do is to explain more generally why different behaviors for different models is observed, and to characterize how a training objective defines information flow in the models. This is important because it can give intuition for creating better training objectives, give intuition of how to properly use pre-trained representations. For example, do we have to take the last layer of BERT or somewhere in the middle, or is the best layer the same for different applications, and so on and so forth. And finally, it could explain different puzzles from previous work. These are some interesting results made in the context of probing tasks which were not explained. I will show you some of them a bit later, and at the end of the talk, we will be able to explain them. So what is going to happen? First, I will explain what I mean by evolution of representations of individual tokens and show the training objectives we use. Then, as promised, I show you some interesting results from previous work we're going to explain at the end. After that, I'll present to you our point of view on the task, the information bottleneck theory. It will be the key component of our work because it will explain the general process which will be seen later with different experiments. Okay, let's start. Our data is text and natural language. Each token has an initial representation, which encodes token identity and its position in the sentence. These representations are fed to a network, in our case, the transformer network. Transformers process input with several layers. At each layer, tokens interact with each other and exchange information. After this exchange, each token receives a new updated representation. This happens until the last layer is applied. After that, some kind of training objective is used to give a signal for training. So what we are interested in is how representation of each token changes from the first layer to the last, and how a training objective defines this process. Note that while we are using transformer in this work, all our experiments will be done in a model-agnostic manner, so we won't actually need details about how transformers work. All I need to understand is that transformers operate with several layers. At each layer, tokens exchange information, and each token receives new representations. So this is everything we need. We consider 3 training objectives. So language modeling, mask language modeling, and machine translation. Now, for each of their training objectives, I will define input and output at each position in a sentence, because we will use it later. So this is standard left-to-right language modeling, where a model has to predict the next token based on previous ones. So here, at each position, input is current token identity, and output is next token. Next task is mask language modeling. In this setting, some tokens in a sentence are selected. Each of the selected tokens is either replaced with a special mask token or random token, or remains unchanged. And a model is asked to reconstruct the original identities of the selected tokens. So, and this is done only in training. At test time, no tokens are selected. So here, most often in training time, representations start from replaced token identity and position, and final layer representations are used to predict current token identity. Note that this training objective forces a model not to over-rely on input tokens and to take information from context. And this objective is especially interesting because this is most of the training objective of BERT. So the last task is machine translation. So here, a sentence encoder processes sentence in one language, top layer representations are passed to the decoder, and the decoder generates translations in the other language. In our experiments, we take only encoder of a trained model. So here, input is again current token identity and position, but actually nothing is reached directly from top layer representations. In this sense, this setting is different from language models. So here, nothing is reached directly, but final layer representations are passed to the decoder. So we saw that each of the model starts from the same representation. And in our experiments, we'll fix model hyperparameters and use the same training data. The only thing which is different is training objective. And while all models start from the same token representation, which consists of current token identity and its position, the way information flows across layers or evolution of token representations is different depending on the objective. And this is our main interest. And now, as promised, I will show you some interesting results from previous work, which used probing tasks and made really interesting observations. So our first one. It was shown that untrained LSTMs outperformed trained ones on word identity prediction task. It means that if we take representations from an LSTM and try to predict token identity of current token or nearest neighbors, then randomly initialized model performs better than trained for language modeling task. Looks a bit interesting, right? Kind of unexpected. So next one, when trying to predict constituent labels, performance of language model layers is non-monotonic, so it goes up to a certain layer, then down, while for machine translation encoder, it improves up to the highest layer. Here we already can see that for different training objectives, patterns of behavior can be substantially different. More recently, it has also been shown that behavior of BERT layers is also non-monotonic. For different tasks, contribution of a layer to a task improves up to a certain layer and then goes down. But while these results are really interesting, so far evidence was somewhat anecdotal and an explanation of the process behind such behavior has been lacking. In contrast, I will try to explain more generally why such behavior is observed. And for this, I propose you to look at this task from the information bottleneck perspective. So information bottleneck theory is my point of view in this work, and now I'll explain you what it is. Information bottleneck is a method from information theory from 1990. It tries to extract compressed representation of input, which retains as much as possible information about output. It operates with terms of mutual information, and it maximizes mutual information with output while penalizing mutual information with input. This is the compression prediction trade-off. But what does it have to do with neural networks and our tasks? Well, this is where it gets really interesting. In 2015, Tishby and Zaslavsky showed that computation in multi-layered networks can be regarded as an evolution towards theoretical optimum of the information bottleneck objective. So a network is moving information about input through a cascade of layers, and this process is considered as a Markov chain. And when a network is moving information from layer to layer, it loses irrelevant information about output while retains relevant. So irrelevant information about output is getting lost. This is what's shown in color in the picture. And so output, in a way, defines partition of input on relevant and irrelevant information, and therefore defines information flow in models. Since outputs are different for each of our models, we expect to see different patterns in behavior. And in the setting, usually the entire layers and entire input are considered, and as you move along layers, mutual information can only decrease. As we'll see, for our setting, this is not the case. So now we'll try to look at the evolution of token representations from the information bottleneck perspective. Here we also view each model as learning a function from input to output. But we look at representations of individual tokens, not the entire input. It means that our situation is much more complex than we discussed earlier. In our setting, information which is retained in representation of a token is induced due to the two roles it plays. First, predicting the output label from two-player representations, and second, preserving information necessary to build representations of other tokens. For example, a standard left-to-right language model builds representations which are not only useful for predicting output label, in this case next token, but also which is useful for building representations of subsequent tokens in a sentence, which is shown on the picture. And this is different, for example, from machine translation encoder, where nothing is predicted directly from final representations. So we hypothesize that the training objective, or the task, defines the nature of changes a token representation undergoes from layer to layer, the process of interactions and relationships between tokens, and the type of information which gets lost and acquired by token representation in these interactions. And now we will first illustrate processes of information gain and loss in representations by evaluating mutual information between a representation of a token and its input token identity. In these experiments, we consider mask language model as a test time without masking out tokens. Also, direct estimation of mutual information is challenging for large networks, so here we had to use an approximation. I'm not going to go into details here. If you're interested, take a look at the paper. Let's come to the results. So first, we noticed that language model loses a lot of information about current input token. Machine translation also, the behavior is similar, but the decrease is much less sharp. This agrees with our expectations, since language model has to predict next token from the top layer representations, and therefore is forced to forget not so relevant current token. Machine translation encoder is not forced to do so. First, because nothing is predicted directly, and second, because token identity can be useful for decoder. But the most interesting and surprising graph is for mask language model. So first, similar to other models, it loses information about input, but then at the two top layers, this information gets recovered. We will refer to this as the two stages of context encoding and token reconstruction. So first, it tries to build generalized representation using context, and then it tries to recover token identity. And note that while such non-monotonous behavior is impossible when analyzing entire layers, here for representations of individual tokens, it means that this information gets recovered from other token representations in a sentence. And now we will come even closer to the information bottleneck setting and evaluate mutual information with both input and output labels. In these experiments, we take mask language model as in training, where some tokens are replaced, and we pick only examples where input and output are different. And when we look at the results, we see that there are actually two processes going on for both language models. Losing information about input, which we saw before, but also accumulating information about output. And for mask language model, these processes are more distinct and can be thought of as context encoding and token reconstruction stages. And this is the key illustration of the information bottleneck principle for token representations. So losing information about input while accumulating information about output. And this is the process will be seen later in different experiments. Next we'll be analyzing changes in the latencies. Well, these mutual information experiments already give insights into processes which shape representations. A direct estimation of mutual information was challenging, and we had to use an approximation. That's why now we'll switch to more well-established frameworks. The questions we ask in this section include how much change is happening in a given layer, which tokens gain more information from other tokens, and which tokens influence other tokens most. We reduce all these questions to a comparison between network representations. In these experiments, we take a lot of data, feed it to a network, and gather representations from some layer. Altogether, these representations form a view of a layer on the data. So we gather different views on the same data and use canonical correlation to evaluate distance between pairs of different views. So canonical correlation finds linear projection maximizing correlation of single directions. And here we use it to evaluate distance between different views on the data. And these views can be, for example, the same layer in different networks. And in this way, we evaluate how different models are. And alternatively, views can be different layers within the same network. And this way, we can evaluate how much change is happening in a given layer. So first, we'll look at the distance between models trained with different objectives. And here we see that the most interesting observation, as I see it, that machine translation encoder and mask language model are closer to each other than each of them to language model. Well, if you don't think about it, it seems a bit strange because you might expect to see that language models are closer to each other. But if you do think about it, you'll find at least two reasons for why a language model is less similar to other tasks. So first, it uses context of only previous tokens in a sentence, while both machine translation and mask language model have access to the whole sentence. And second, language model focuses on building representation of some other tokens, and in this case, next token, while machine translation encoder and MLM focus on the current token. So, and next, we evaluate how much change happens in different layers of the models. Here we see that for machine translation, the amount of change decreases from layer to layer. It means that machine translation encoder kind of refines representations as you go from layer to layer. For language model, we see a lot of change at each layer. And this is kind of intuitive because we saw that language model, so what the language model does, it forgets information about input token and tries to build a representation of output token, which is different from input, right? And this process requires a lot of change in all layers. And for mask language model, we again see the same two stages, context encoding and token reconstruction. So first, on context encoding stage, the amount of change goes down. So there's like generalization stage where contextual information is accumulated. And then at the token reconstruction stage, we see a lot of change because the model forgets information about context and tries to reconstruct the regional identity of a mask token. Okay, and now we'll look at the amount of change and influence for tokens of different frequencies. So we know that tokens in a sentence interact with each other. In these interactions, they can play two roles. On the one hand, they can influence others by giving some information. On the other hand, they are influenced by others. It means that they consume information and change themselves. So when we talk about token change, we mean how much representations of these tokens change between layers. When we say influence, we mean how much representations of other tokens which change if we exclude current token from interactions at a given layer. So if I am not here, how different would you all be, right? So this is how we evaluate influence. So first, let's look at the amount of change. For machine translation, we see that frequent tokens, the red ones, change more than rare. The same for language model. So frequent tokens change more than rare. It means that they consume more information. And patterns are for machine translation and language model are similar, but the only difference is on the last layer. For language model, we see roughly the same amount of change here. We can speculate that maybe transition from current token to next on the final layer where it tries to build representation of next token requires roughly the same amount of change for all token types. And for MLM, the behavior is again the most interesting. And we again can clearly see the same two stages of context encoding and token reconstruction. What is also interesting that transition from this generalized representation to recreating token identity requires more change for rare tokens. And now let's come to influence. So with influence, the behavior is similar. So as you would expect, rare tokens influence more, and for language model and for mask language model. So takeaway message is frequent tokens change more, rare tokens influence more. Right? So if you're a rare token, you have a lot of information in yourself, and you don't change much keeping your information, but you influence others a lot. But if you're a frequent token, you don't have much information in yourself, and you try to consume a lot of information, but it changes you a lot. It's kind of makes you think what kind of token you are in your sentence. At least it makes me think so. Okay. And in the last part, finally, we'll try to look at which properties are most important for ordering representations in space. So now we'll look at the feature space, and we'll look at how these representations are physically located in the representation space. As you remember, all models start from current token identity and position. And since we are going to use these representations on downstream tasks, first we'll check how this information about current token identity is preserved in different models. We do this by looking at closest neighbors in the representation space. So what we do is we take a lot of data, gather representations of different tokens, and then for each token we look at the closest neighbors. Then we evaluate a proportion of neighbors which have the same token identity. And here we see a graph which is exactly the same like with mutual information, right? So language model forgets current token a lot, machine translation encoder forgets but a bit less, and mask language model preserves token identity better, and we again can see these two stages of context encoding and token reconstruction. And I also have a visualization for you. So we get that different occurrences of tokens is, are, was, were, and visualized their t-SNE projections. So here we see that as you go from layer to layer, from left to right, you can see that language models confuses between representations of these tokens a lot. And it's a complete mess on the final layer. For machine translation, it also mixes them up, but to much less extent, and you can still clearly see the difference between different clusters. And mask language model preserves token identity almost perfectly. So here clusters never mix up, not in any layer. And we also took some tokens which were replaced here. So this originally were tokens is, are, was, were, and as in training stage, they were replaced with a random token. So here they're clustered together and the model does not understand what they are. But as you go from layer to layer, you can see how it tries to disambiguate them. And at the final layer, it actually gets pretty good. Well, so far we looked at how current token identity is preserved, and now we'll look at how left and right context are preserved in different models. We'll look at lexical context, and for this we'll look at identities of adjacent tokens, which means immediate left neighbor and immediate right neighbor, and also syntactic context. For syntactic context, we'll look at CCG text, which encodes syntactical information of this token. And these CCG texts are especially convenient in our setting because we can split them into left-right, left part, which encodes left context, and right part. The results are really similar for both experiments, so I only tell about one of them. So for lexical context, we can see that language model forgets information about left context while tries to build information about right context. So accuracy for right context for language model is low, of course, because it doesn't have access to right tokens in a sentence. But it still improves up to the highest layer. This is the same process which we saw before with mutual information, right? Losing information about input while accumulating information about output. And for syntactic context, again, pattern is similar. So language model tries to accumulate information about right syntactic context, about context of future, which it doesn't have access to. And for mask language model, it goes up, then down. And we can see, again, these two stages. So when it goes up, it means that it encodes contextual information. And at the token reconstruction stage, it goes down. And this is, again, a visualization. So here we see that language model is not really good at clustering by syntactic information, because here we take like a full CCG tag, which encodes both past and future information. And language model, of course, it doesn't have access to future and it cannot recover it very well. For machine translation, it improves up to the highest layer. And for mask language model, it's almost perfect on the first layer, and then it gets a bit worse on the token reconstruction stage. And finally, now we'll again look at the same results from previous work, and we'll try to understand them. So first, untrained LSTMs are better for token prediction than trained for language modeling tasks. Of course, because language model is forced to forget current token identity. It is forced to forget contextual information. Next one, for when trying to predict constituent labels, machine translation encoder behavior is monotonic, while for language model is not. Well, again, we saw this. So machine translation model kind of refines representations, so it improves up to the highest layer, but language model loses information about input and tries to accumulate information about output. And therefore, it forgets information about constituent labels of the current token. BERT layers, again, now it's clear that these are two stages of context encoding where contribution of all layers goes up, and then token reconstruction where all this information is getting lost. And there are a lot of different other works which also show similar patterns, but I want to show you only one of them. It's a recent work which was accepted to ECLAIR this year. And I like it more than the previous ones because it actually tries to use BERT for not just understand what it learns, but to use it for practical applications. So here the researchers tried to use BERT representations to build a metric for evaluation of text generation. Instead of, for example, they used it for machine translation instead of BLUE score, because BLUE score, it's n-gram matching. And what they tried to do is to use kind of semantic similarity to measure how good is translation quality. And here they look at different layers and evaluated how good this metric correlates with human judgment if we use different layers of BERT. And we again can clearly see that performance goes up at context encoding stage, and then it goes down on token reconstruction. So if you're trying to use BERT in some applications, you probably might want to use representations from somewhere at the end of context encoding stage, and not the final layers where this information is already lost. So finally, conclusions. We find that for language model, evolution is a transition from known past to the known future. Mask language model initially acquire information from context, then they create token, and this happens in 2 stages of context encoding and token reconstruction. And for machine translation, representations get refined with context, but most of the information is preserved. And our contributions. We propose to view the evolution of token representation from the information bottleneck perspective. We conduct a series of experiments supporting this view, and we relate to some findings from previous work, trying to explain them. If you want more details of visualizations, here's an official blog post on my page. And if you are interested more in the mechanisms transformers can use to encode information, I have also a blog post for our other paper. It's ACL paper, The Heads. And by the way, one of my students who wrote this paper is now master student at EPFL, and he's now here, which I'm really happy about. And that's it. Thank you.